All right. Well, why don't we get started? Um, uh, my name's Joe Castiglione from the Zephyr Foundation. I want to welcome you all for being here today for the second in a series of four Zephyr learning sessions on the GMNS standard. Our first was back on May 7th, and that was on the standard itself. You can find a recording of that as well as the presentation on the Zephyr website under the events page. But today we have Andre Carroll from The Ohio State University and Dave Dixon from MORPSI. We're going to be discussing using GMNS for calculating multimodal accessibility metrics. So with that, I'll hand it over to Andre.
Thank you very much, Joe, for the introduction. Yeah, welcome everyone to this webinar. This is, as Joe said, mostly about the application and use of GMNS Plus in practice. So we will be presenting the results of a pilot project that we did on green space accessibility here in the Central Ohio region. Quick overview of what we're going to talk about. First, we will spend about 15 minutes with an introduction. We have a very brief high-level introduction to GMNS Plus and to the goals of this project. And then after that, once we've formulated the goals and talked about the questions that we were looking to answer, we will move on to talk about the workflow, how our team specifically addressed the accessibility analysis question or the accessibility related questions with the toolkit that we had available and the data in GMNS Plus standard. And then after that, we're going to move on to about 15 minutes discussion of the results of the project, followed by approximately 20 minutes that we're allowing for questions and discussions at the end. So if you have any questions, please do put them in the chat. We're going to be monitoring the chat, and we'll keep the questions for the end of the webinar then. Also, we would like to invite you to answer a couple more questions that we have for you. So when you joined, there was already a little poll up. Now here you've got a QR code and a link to your right. So there's a couple more questions, things that we're interested in and that we will return to when we move on to the Q&A. All right. So with that, let me do a brief introduction of who we are. This pilot project that I'm about to talk about, that I'm going to introduce you to. The lead team behind this is me, and I'm an associate professor at The Ohio State University in City and Regional Planning and Civil Engineering. And my colleague, Dr. Harvey Miller, who's a professor in geography and the director of the Center for Urban and Regional Analysis at OSU. And here at OSU, we partnered closely with our local MPO, MORPSI, the Mid-Ohio Regional Planning Commission, and specifically Dave Dixon, who is the Director of Analytics and Strategy at MORPSI, and who's going to say a few words as well in a couple of slides when we talk about the project more specifically. Then we have a fantastic team that's been doing all the analyses and the work behind this. So we've got Karen Kurdolf, a GIS manager at Cura, and then Manoush Mostafavi and Jaeyoung Kong are both graduate research associates here. Now, the work that we're presenting, this was done in the context of a grant that is funded by the National Science Foundation. The grant is led by the Arizona State University, Dr. Shushong Zhou, and has us as a partner institution, the Ohio State University, as well as the Metropolitan Transportation Commission, the San Francisco Bay Area. Now, before we start talking about GMNS Plus and the application of GMNS Plus, definitely also we want to acknowledge here all the fantastic work that has gone into the actual development of the data standard by the USDOT, Volpe Center, especially Scott Smith and Ian Berg, and of course the Zephyr Foundation, which has been instrumental in coordinating this work and building a community around the development of the data standard. All right, so let's do a brief high-level introduction to GMNS Plus. What is this? So GMNS Plus is an open data standard for transportation networks. It is explicitly multimodal and captures automobile transportation, walking infrastructure, biking infrastructure, and public transportation, and is able to go down to a fairly microscopic resolution in representing different aspects of the infrastructure, including segments, lanes, signals, and even time variation in the configuration of the network. So the idea behind GMNS Plus is to specifically support multi-resolution modeling and multimodal modeling, and to have an open and common data standard that is agnostic to the specific application that it's being used for. So one of the nice things about a data standard like this is it integrates with common software and data sources. There is a Python-based toolkit to convert between common data formats, common file formats, and the GMNS Plus format. A lot of that toolkit is maintained by the team of Dr. Joe at Arizona State University. And I do have some links at the end of the webinar, so we will post this publicly as well. And any network that we develop that's encoded in GMNS Plus can be visualized with common GIS software. So there's very much interoperability between this data standard and and common software that MPOs, agencies, practitioners use in day-to-day in their day-to-day work. Now, if you want to learn more about the standard, I encourage you to take a look at the Zephyr Learning session from May 7th, which was done by our colleagues from the USDOT Volpe Center, specifically Scott Smith and Ianberg, who have a fantastic session that really goes in depth on the technical details and capabilities of GMNS Plus. So way more than we are discussing here today. So for a practitioner, for an agency, if you're in consulting, a transportation professional, what are the advantages that we see of adopting the GMNS Plus data format? Well, compared to data formats that are based on proprietary or custom-built software, the GMNS Plus really reduces complexity in our workflow. And it does that by really facilitating the exchange, the sharing, the pooling of data between agencies, between collaborators, across jurisdictions. So by kind of having everything in a common open source data format, it becomes much, much easier to send data back and forth. It also makes the preparation of data for applications, for analyses, for modeling a lot easier. And supports the reusability of data across applications. So we're no longer having to develop data formats that are specific to one certain application or one model that we're working with. It becomes much more universally usable across many different applications, and that, of course, supports comparability and interoperability. And then finally, the advantage of a data standard is also to help us maintain institutional knowledge about our data, right? So it reduces the learning curve for anybody new who joins a team, who joins an agency or an organization, to learn about the data that are being generated and maintained within that organization and how to manage those data and work with them. Now, one of the big advantages, and this is really what we're going to talk about a lot today, is that GMNS Plus supports multimodal modeling. And so specifically what that means is that with GMNS Plus coded networks, we get fully routable multimodal networks. And that really allows us to capture complete door-to-door trips. So for instance, if we're considering multimodal transit travel, that allows us to not only capture the part of the trip that happens on board of a transit vehicle, but also the access and egress segments that may happen by other modes. This is also something that could be very advantageous for the modeling analysis of shared micromobility systems, for instance, where somebody may be traveling part of the way with a shared scooter or a shared electric scooter or shared electric bicycle, but then combining that with walking or even with transit. And so, as we're going to discuss with the examples that we're looking at, in such intermodal trips, multimodal networks, we can incorporate things like wait times and transfer times between modes. And this sets it apart from existing approaches where oftentimes because of the kind of siloed networks that we're working with, we end up having to analyze travel by different modes separately. So with that, I want to introduce us to the case study context. So this is the specific project that we will be talking about for the rest of this webinar. So the overall goal that we had, what we set out with was to develop a case study to demonstrate the use of GMNS plus coded data in a real-world context, and specifically demonstrate the value of having this multimodal routable network. And so the specific question that we're looking to answer is about multimodal accessibility to green spaces and parks in Franklin County. Now, Franklin County is the county that the city of Columbus metro area is located in. We have a map here in the middle that shows us the situation. So you can see down here, bottom left, this is Ohio. We can see Central Ohio. And so the area that's in gray here, that's what's shown a little larger here. So we've got Franklin County. This is what we're going to be looking at a lot of maps of Franklin County. And so Franklin County contains the majority of the city of Columbus and surrounding cities. And the Mid-Ohio Regional Planning Commission, MORPC, acts as the MPO for the city of Columbus, for the Columbus metro area. Now, surrounding Columbus are several other counties that are part of the MORPC area. Within some of those, MORPC acts as a rural planning organization. And so that together is the Central Ohio region here centered around the Columbus metro area. Now, within Franklin County, so within the urban area of Columbus, we're looking to understand multimodal accessibility to green spaces and parks. Now, beyond that, our partners at MORPC were also specifically interested in comparing the access between two types of areas. And so I'll let Dave say a little bit more about this in a second. Let me just introduce the map here. So this is comparing the accessibility between 452 traffic analysis zones, TAZs, that have been identified by MORPC as environmental justice target zones. So those are shown over here in a darker color. And so these are areas with higher poverty rates or higher levels of minority population, and to compare access to green spaces and parks between these what we call EJ TAZs, environmental justice target zones, to the remaining areas of Franklin County. All right, so with that, we do have our colleague Dave Dixon here in the webinar with us. So we'll switch over to him for a couple of minutes just to give us a little bit more background and motivation on MORPC's interest in these analyses and what we're doing.
Andre, thank you very much for that introduction and for sharing a little bit of background on our organization, the Mid-Ohio Regional Planning Commission, and how we feature in this project. First of all, I would like to just thank Andre and Harvey for their great work on this and their team's great work on this and being very collaborative. One thing that they make clear from the very beginning is they wanted a real world compelling use case for this project. Something that folks would find value in the outputs beyond just the value in the methods and the tools that were used. So that they could have that holistic look at what were the data inputs, what were the methods and tools used, and what was the result. They also paid careful attention to documentation and looking at the lift that would be required, as there's an end goal to promote this as something that other MPOs and other transportation planners can take and can use. A lot of the benefits that Andre highlighted on the previous slide accrue at higher levels if you have a large number of stakeholders, taking advantage of this data format and taking advantage of these tools. So for Morpsey's part, first I'll talk to the why, park accessibility. Why do we choose park accessibility? And then I'll talk a little bit about some advantages to the tools and methods that they employed compared to our historical approaches and the limitations of some of the other tools that we have in-house. So first off, we pay great attention in our plans to whom benefits of infrastructure and amenities accrue. As I'm sure most of you on the call are aware, Some things are driven largely by zip code or distance from a city center, or whether you're in an urban area or a rural area, all sorts of different factors which can impact residents' access to different types of, again, amenities. Parks are hugely important to Morphe in our planning efforts and green spaces. One of the things that we consistently do is try to build out, is to support active transportation via building out a network of sidewalks and trails. We have a regional trail network, which we call the Central Ohio Greenways. Those not only promote active transportation, but specifically aim to connect people through and to green spaces around the region, to something that which we feel is very important for community health. We also support our efforts to expand transit and transit access around not only Franklin County, but the greater region. So the TAZs, or traffic analysis zones, are our standard geographies that we use when evaluating transportation projects. So it's important to us that the results be able to be presented in those geographies. If you were to look at our long-range transportation plans and other plans we do use to, this is our standard geographical areas that we assess the impacts of any intervention. So this allows us to consider access to parks in very much the same way. Now, to the methods. Traditionally, we look at vehicle trips, or we look at transit access by being along transit lines or proximity to bus stops. And we will look at buffers from a TAZ, or we'll look from a TAZ, or we'll look from a facility out to see how many TAZs can be reached when we do these types of accessibility analyses. So historically, when we've looked at access to jobs or education centers, uh, shopping, and other facilities, that's how we've done that. When we have done analyses for our member communities, of which there are almost 100 local governments who are members of MORPC, we have a separate tool. It's not a travel demand modeling tool, but it's an active transportation network analysis tool. It's a great tool, but the way that works is essentially we can pick up to 1,000 points, and we can simulate access along road networks, along sidewalks, along multi-use paths, and we can generate some population demographic metrics for the population served. So for example, we would go into the community, they would say we have these 5 parks, and we would tell them which percent of their residents are within a 10-minute walk from the parks. And then we could show them gaps that they have to use in their park planning. This is different. This allows us essentially to go back to lean on that aspect of the multimodal navigable network to actually look at how any resident from a given TAS can access these parks via walking, biking, transit. The use cases that we considered, I think we did walking alone, biking alone, walking to the bus, and biking plus bus, and then compared that to car alone. I'm not sure if all of those are featured in the presentation, but that is something which we previously did not have the ability to do. So the two big benefits are in terms of the use case, it created an opportunity to get a lot of great collaborators involved to look at an area we had not previously looked at. And we were able to explore some new methods, which allowed us to really get a more realistic look at what options are available to residents by virtue of those mode switches, which is not something that our other tools currently allow us to do. So Andre, thank you for teeing this up really well, and I'll stay on if folks have questions later.
Excellent. Thank you very much, Dave. Right. So with that introduction, now that we've talked about the sort of the bigger context of the case study and MORPC's interest and involvement in it, let's orient ourselves a little bit more in terms of what are we talking about in terms of this park infrastructure that we're interested in. We're interested in access to the parks. So around Franklin County, around Columbus area, we have an extensive system of parks and green spaces. Now, here on the right-hand side, we can see a map that shows 4 principal types of parks. We're omitting some of the very small ones here. But it's divided up into, we can see the neighborhood parks, the red ones, they're very small ones, community parks that are also fairly well distributed and on the smaller side. And then the regional park system and the metro park system, in particular, the orange and the green ones that tend to be larger parks, but also a little more located on the periphery or along certain corridors here, the Central Ohio Greenways. So on the left, we have a breakdown of the acreage here. We will be looking at, in terms of results, we're going to be looking at access to total acreage of park space or park lands. So just as a way to orient ourselves a little bit, the community parks and the neighborhood parks, as we can see here, these tend to be really on the smaller side, especially the neighborhood parks, whereas these regional parks and the metro parks tend to be more on the 25 to 100 or 100 plus acre size range. And so in terms of counts, even though about 50% of the parks, so about 50% of the parks are less than 5 acres, but in terms of the total amount of park area, that actually is less than, about 5% of the total acreage of parks. And so that the total acreage is really driven largely by these very large parks that we see here. So again, the regional and metro parks. And so the reason why this is important, we can see that the neighborhood parks we're not going to worry about too much more in the analyses that I'm going to present. So part of what we'll talk about is access to community parks. These are sort of the more evenly distributed here, kind of small, medium, and some larger size ones. And then the regional parks that tend to be a little bit on the larger side, and especially along the greenways that Dave mentioned. So now that we've understood what the objective was and the question that we're trying to answer, first I want to spend some time talking about the workflow. How did we actually go about conducting this analysis? And the intention here is to also illustrate how this works with a GMNS plus data format and sort of serve as a blueprint for how another organization or MPO might go about an analysis like this as well. There we go. All right, so step number one, we have 7 steps total that we're going to outline. They are generally specific, or the examples that I'm giving are specific to our case study here in Central Ohio. So step number one, the data acquisition and preparation. For what we wanted to do, we needed network data. So a lot of the data we obtained from MORPC. This included sidewalk infrastructure, as well as we also got some data from OpenStreetMap on pedestrian infrastructure to fill in some of the gaps there and add crossings across streets. And then a not really bike infrastructure, but a very interesting data set that MORPC maintains, and we're actually going to talk about that in one of our examples, which is called the bike level of traffic stress data. So every link on the network is assigned a level of traffic stress representing how stressful, in a way, we would consider that link to be biked on. So like I said, we'll look at this a little bit more in detail later on. So what I do want to mention for some of the analyses that come up front, free flow speeds for each link are assigned for bicycles are assigned based on these level of traffic stress, on the level of traffic stress levels. Then we have a set of multi-use paths, including the Central Ohio Greenways. Something that we're very proud of here in Central Ohio is we have an extensive multi-use path system around the city that connects throughout the city. We can see a little map down here of the Central Ohio Greenways, both the existing and the projected ones. Then we got coded data. Of course, this is about multimodal accessibility, and transit is a big part of that. So we obtained the most recent GTFS files from our Central Ohio Transit Authority, as well as the auto network, which is data that comes from OpenStreetMap. In addition to that, of course, we had some shape files, so some polygon files here, parks and open spaces, the one that I showed before, the traffic analysis zones, and then we also brought in some socioeconomic data, which we drew from the American Community Survey. So for all the networks, at this part, this is the start of the multimodal journey. We have separate networks for pedestrians, for bikes, for transit, and for automobile. Each of those networks having its own node and link data set. So before we turn this into an integrated multimodal network, we have to choose a multimodal representation option. So for those of you who were in the webinar last month, the GMNS Plus webinar, this was discussed a little bit already. So GMNS Plus has two ways in which we can represent a multimodal network. On one hand, we could have a set of shared links for multiple modes here on the left, where we have one single network with links and nodes, and each link will have an attribute called allowed use, which defines which modes can be used on this link. So a single link then is used by multiple modes. And so this is the type of network representation that is good for when we're generating network from a single source. On the right-hand side is the alternative, which is to have separate networks, one for each mode, that are overlaid on each other and connected by transfer links. So for example, in this image, this figure, we're showing auto network and the walking network and the places where you could move between the auto and the walking network. And so each mode here has its own set of links and nodes. This requires the generation of additional connectors, but this is more, I'd say, natural to work with this representation if we have our data from multiple different sources. And so given that we were pulling together multiple different data from many different sources, this is the representation that we chose. And we'll talk a little bit more specifically about the connectors and transfer links here. Okay, now step number 3, this sort of goes without much explanation, but we have to, for each one of the modes, we want to convert the network data in the format it came in to GMNS Plus. So the pedestrian and biking network and is GIS data, the roads, the additional pedestrian links from OpenStreetMap, trans as GTFS. For each of those, there is a conversion tool. This is the Python library that I mentioned beforehand that is maintained by our colleagues at Arizona State University. And that provides an extensive set of Python-based tools that allow easy conversion between these specific data formats and a unified GMNS Plus format. Now, in GMNS Plus format, again, we have a node and a link file for each of these. So they're not integrated yet at this point. That's still to be done. Separately, the traffic analysis zone. So we have a Python script that is provided by us, the Ohio State University, that extracts these and generates the zone centroids, which is what we need to connect individual zones to the network. Now, step number 4, this is still before the integration. So here we're still working with separate network files for the various modes, is the renumbering, the generation of connectors, and the generation of transfer links. So the first thing that we have to do is to choose a base network. Generally, this will be the slowest mode, the mode that serves for access and egress to other modes. So that'll be walking or biking, depending on what you're interested in. In our case, we were running multiple types of analyses. So in some cases, we had the walking network as the base and other the biking network. And so that's our base network, and the other networks will then be merged into this base network, technically speaking. Now, before we do that, because remember, we're still maintaining, in this case, biking, pedestrian, transit, and automobile. So we're still maintaining separate node and link files. First, we have to for the non-base networks, we have to renumber the nodes and links to avoid conflicts once everything gets merged together. And then we need to generate bidirectional connector links that connect. Now, these are the red ones that are shown here that connect the centroids of the TAZs, of the traffic analysis zones, to the nodes of the network. And so because we're interested in access from the various zones, we're choosing the centroid as representing the source of demand for each zone. So here, the gray area, the gray shaded area, that would be our zone. It has a centroid, and then we have to generate these connector links between the centroid, the source of the travel demand in this case, and nodes on the network from which people would then progress on to their destinations. So now the centroids, these are going to be variable length connectors. We would assign walking or biking based travel times to those, or travel speeds. And generally we want these to be high capacity links that are not flow constrained in any way. Then in addition, we need to generate transfer links. So these are in orange here. We have transit stop node in this example, and this is now shown as bike link, the black one. And so somebody who wants to, say, transfer from biking to transit, they would have to move on this transfer link to access the transit stop and then board the service. There's an additional boarding and lighting link that is shown here that is part of the transit network. And so one of these, so either transfer link or the boarding and lighting link, we can incorporate transfer penalties. So to reflect waiting times or transfer times to make the movement between modes realistic in terms of timing. Now, we're actually going to see an example to illustrate this later on, but I do want to mention ahead of time the connectors and the transfer links. Obviously, this is something generated by the user. And so the design of these, how we choose to create them, what radius we're connecting nodes in, how many nodes we're connecting, this can really influence the results. And we do have a bit of a little illustration to dive a little bit deeper into this point. So as step number 5 then, this is now where we really merge all the networks. So we've prepared everything, we've got the connectors, transfer links, and the renumbered individual files. So we're going to merge all the networks here by combining the node and link tables into one single table for instance, auto, walking, biking, and transit. We do need to sort the links to maintain a forward star structure so that we maintain a routable network. So here's just some illustrations from our case study. This is, as a matter of fact, this is the center of the OSU campus up here, the academic campus. So we've got the transit network around campus, just this is derived from GTFS. We see here in transfer links in orange, bus to bus. And then we've got the bike network over here. We can see the centroid connectors in red. And so we merge all of this together with the added connectors that are shown in this enlarged little picture here on the right into a single merged network. And so practically speaking, like I said, that's just then the combined node and link table. And then finally, before we can use this network, this integrated multimodal network for our analyses and for modeling, we do need to do some validation. So this is a two-stage process, the validation. The first is a structural validation. So there's a GMNS ready toolkit that's also provided by our colleagues at Arizona State. The link will be at the end of the presentation, and we'll post this publicly. But so it's called the GMNS ready toolkit, which runs a set of, it's 3 levels here, screenshots on the right. Runs a set of analyses to just verify that all the zones are connected, all the references are valid, the links properly connect to the nodes, etc. Now, beyond that, though, this is not checking the parts that are more that the user with their expertise will have to be able to judge, or will have to judge whether they're realistic or not. So then we move on to the accessibility validation, the second stage. Now, for accessibility analyses on a GMNS coded network, we used a tool called DTA Lite, also provided by the Arizona State University, by our team led by Dr. Susong Zhou. And so this is an open source, cross-platform, lightweight, and fast Python path engine for networks that are encoded in GMNS+. And it does actually have a module and functionality that allows you to perform accessibility analyses within the toolkit. So the first thing, and this is what we consider a second stage of the validation, is to just perform an accessibility analysis that's not really meant for generating results, but more for verifying that the travel times are realistic, that routes are realistic, and to confirm that the network is fully connected, right? So that there are no islands where somehow parts of the network are disconnected if they should be connected in reality, right? And so this is then up to the user. In this case, we did several iterations on our end, several hours of like verifying the results, checking that everything is realistic, that everything is connected in the way that it should be, before we can move on to the actual full-blown analysis. And so then finally, as the last step, this is what I'm labeling as step number 7 here. Once validated, we use DTA Lite again now to perform accessibility analyses using this integrated routable multimodal network that we have created. Okay, so with this introduction to our workflow, Let's move on to look at some results of our analyses. So this is our Central Ohio case study. Now, I want to say before I dive into this, there's still work in progress. The project has not ended yet. We are still in the process of working with MORPC and generating analyses and results that will be in the final report. But I want to give you a glimpse here of some very interesting results that we have derived and that we think are nicely illustrating the use of the GMNS Plus network format and the tools available to analyze multimodal networks. So before I dive into the individual results, so I'm going to have 4 questions and results that I'm going to show in the following slides. Before I go into this, I do want to point out something, which is we're talking about access to green space and parks here. Now, on the right-hand side, we can see a comparison. These maps show the total acreage, so total park area of one type of park. This is community park. So you might remember these are mid-sized parks that are distributed throughout the county. So the total acreage of park area that is accessible within a time budget from each zone by different modes. And so at the top, we have automobile within 15 minutes, right? So the darker shades, you have within 15 minutes more acreage available to you that you can access by automobile. And at the bottom, we have transit within a 30-minute time budget. We're considering transit schedules here 2 p.m. to 4 p.m. on Saturdays. That is important for the accessibility analysis. We did have to specify when we're considering this. Weekends, we thought that's when people probably will be more likely to want to go to parks than during weekdays. So this is for Saturday transit schedules. And really the only point that I want to make here is just, for those of you not familiar with Columbus, it is very auto-oriented. And so we can see at the top, if you have a vehicle, if you have a car in Franklin County, you will not have a problem accessing large amounts of parks and green spaces within a fairly reasonable time budget. Conversely, if you do not have a car, now we have to worry a little bit more about sort of what those spatial patterns are of accessibility or lack of accessibility to recreational opportunities and to green spaces and open spaces. So with that, let's move on to the first question. So the first thing that I want to illustrate here, and this is going back to the one of the steps in the workflows, is let's dive in a little bit more to the question: what is the impact of the zone connectors? So what we're going to look at in the next page in the results is accessibility for 2 different cases. So if I am considering travel by transit, I can connect the transit network to the centroids of the zones and the centroids as the access points to the parks in 2 different ways. On the left, we have what I would consider a simplified transit network representation that is not truly multimodal, where we simply have these connectors. So we're connecting the centroid directly to the nearest transit stop, and then we're connecting the access point to the park to the nearest transit stop there. Right. So in that sense, it's unimodal, right? I have all I really am modeling in terms of like actual travel, so to speak, is when somebody is on the transit vehicle. And so on the right-hand side, we now have an integrated walk and transit network. And so from the centroid, somebody is routed along the walking network and then accesses the transit stop that is most easily accessible in that way. And same on the other end, where they then go to the park. For both cases, so for the connectors and for the walking network, we're assuming an average walking speed 3.1 miles per hour for both cases. And the question we asked was, how does this impact, so the fact that we can do this multimodal access to transit by walking, how does this impact the modeled accessibility to green spaces? Let's take a look at this. So here's result number 1. And on the left-hand side, and again, we're looking, this is the same scale that we saw beforehand. So total acreage of community park area accessible from within each traffic analysis zone. On the left-hand side is a simplified transit network representation with these connectors. On the right-hand side is an integrated walk and transit network. This is both using 30-minute time budgets and again, Saturday afternoon transit schedules. And so what we can see here, there's not really a clear increase or decrease in terms of the park area available, but rather if you sort of zoom in and scrutinize individual zones, you'll see that some zones gain accessibility, some lose accessibility, modeled accessibility, right? And so what this really leads us to find is that if we're just using the representation, simplified representation with connectors, compared to the integrated actual modeling the walking access and egress, we're introducing biases, right? Some zones, it's going to look better. Some zones are going to look worse than in reality. And so we decided to dive into this a little bit more, a little deeper to illustrate what's going on here. So we have an example here with the OSU campus area as an origin. So this is the one that I introduced beforehand. We've already seen this one. But from the OSU campus area, we looked at the travel times to a large set of parks throughout Franklin County. And on the left-hand side here, the scatter plot. We can see on the horizontal axis, we have travel time with a simplified transit representation versus integrated walk and transit travel time on the vertical axis. So in the scatter plot, you can see a 45-degree line, right? This is where the two would match perfectly. If a data point is above the line, that means the walk and transit is resulting in a greater travel time than the simplified representation. If a point is below the 45-degree line, then the simplified representation is resulting in a greater travel time than the walk in transit. And so we have two comparisons over here on the right to illustrate how this is happening. So A is a case where the simplified representation is faster. And so what's happening here is that this connector is going from the zone centroid to the nearest transit stop, but it's actually a route that is not directly walkable, right? And so the distance that somebody has to walk until they get to the transit stop, that will actually be longer if we're considering the true layout of the walking network. And as we can see here also, somebody would actually end up getting on the bus at a different stop because this one on the left is not the optimal stop to get on if you really are walking on the walking network. And so what that results in is in the simplified representation generating a shorter travel time than when we really consider walking access and egress. On the right-hand side, we can see another example where the opposite is the case. So here the simplified representation is generating a longer travel time than the integrated walk and transit. And so at the top, you can see there's the same origin here. We have the connector. There's a different transit route that the person gets on. And then over here is the park they're going to. And so there's the connector to the closest transit route, transit stop, or one of the closest ones. And so it's forcing people onto actually two transit routes with a transfer in between. Whereas in reality, if you were walking here, the optimal and the fastest route would involve a lot more walking and only one transit link or transit connection that you would take without a transfer. And you can see here, right, these much longer walking paths. And this is the problem here is this is not being captured by the representation above because the stop where the person would get off is actually quite a bit farther away from the park than a whole number of other stops on the transit network. So it's not a natural connection to make to that one. So what that means is that the simplified network is generating a greater travel time than in reality. And so these two cases together, this is how we see how in the previous example, right, some zones end up gaining modeled accessibility and some end up losing modeled accessibility. So the walk network, that's what we would consider sort of the actual true accessibility, right? So let's move on then to question number 2. And this is about the access and egress mode. So the question we're asking here is, does the ability to take the bike on the bus expand access to regional parks in Franklin County? So we're switching over from the community parks to the regional parks, larger park system. The entirety of the CODA network or CODA fleet is equipped with bike racks on the front. And so the question is, well, okay, if you are a little limited in your ability to access, say, this regional park system by walking in transit, what happens if I were to model being able to take my bike on the bus? And so here's the result. It's quite striking, really. So we see the total regional park area accessible within a 30-minute time budget. The acreage is shown here. And so on the left is access and egress by walking, right? And we're comparing this on the right to access and egress by bicycle. And so what we're really seeing here, what this illustrates is that, well, like I introduced at the beginning when I showed the car accessibility, right? There is a significant penalty in terms of access to recreational spaces and green spaces if I do not have access to an automobile in Franklin County. But we can see that really just the ability to take the bicycle on the bus and combine biking with transit within this 30-minute time budget is that really vastly expands the amount of, in this case, regional park land that I'm able to access without a car. Now, one caveat about this analysis on the right, where we see this vast expansion of accessibility, is that we are allowing bicycles on all roads here, except those where bikes are explicitly restricted. For now, we will return to this question or to this issue with question number 4. Now, before this, let's move on to question number 3. So here we're going to look specifically at the issue that was raised with the environmental justice target zones that we introduced at the beginning of this webinar. So the question that we tried to address here was, does average travel time to the nearest park differ between the environmental justice target zones, the TAZs, and other TAZs? And does this differ across transportation modes? And so for this analysis, we're really pulling together community, regional, and metro parks. So the mid-sized to larger parks, including this metro park system, that is the Orange Park system around Franklin County. Just as a reminder here on the right, we can see the distribution of the EJ target TAZs. And one thing that was sort of interesting to us in this analysis was, as you can see, the EJ target TAZs generally, they tend to be a little more, in many ways, a little more concentrated in somewhat more densely populated areas, whereas the larger parks do tend to be on the periphery of the urban area. And so we wanted to see how access would differ. Now, the average travel time to the nearest park is what we are considering here. So it does, in effect, we are not taking into account the differences between the parks, at least in this analysis that we're presenting, but we're really just looking at how long it would take you on average from any given starting point until you can reach a medium to large size park for recreational purposes. And so here's the result. Now, this is by different modes, right? And so here again, a nice thing is we have this multimodal routable network, and we can really do a head-to-head comparison of the different modes traveling on this effectively same network. Right? So what this is showing, this bar chart that we have on the left, is the weighted average travel time. And so we're weighting by population here to kind of even out like urban versus suburban zones. So the weighted average travel time to the nearest park in minutes, considering community, regional, and metro parks. And we can see car alone versus walk in transit, bike in transit, and walking alone. Now, what we see here, a few remarks on this. The first is that access to green spaces, I mean, clearly you can see the penalty of lacking auto access, right? Is that with a car, we're generally around 5 minutes or less to the nearest park. Whereas without a car, we're typically looking at roughly double that time, if not even significantly more. Bike and transit remains the most efficient non-automobile option. But what we can also see if we compare the EJ TAZs, which are the darker ones here, to the lighter ones, that as a matter of fact, even after waiting for population, the EJ TAZs actually have shorter travel times to parks compared to the non-EJ zones. Now, many of the EJ zones are located in denser urban areas versus suburban areas. And so that might be helping here because also denser urban areas might have more, especially community park infrastructure. Remember that this is looking at the travel time to the nearest such park, right? This is regardless of what type of park it is. So we do see sort of consistently that the EJ zones do have better access in terms of shorter travel times to the nearest park. We also do see that actually walking in transit, at least in this analysis, barely has an advantage over walking alone, right? Now, one caveat here, of course, we're really just looking for the nearest park, so we're not accounting for park quality or park size. We could expand this analysis by thinking about by specifically accounting for park, the type of park, or the acreage, the size of park, and see whether that would change anything in the results that we're considering here. And that brings us to the final question that we want to use to illustrate our work here. And this is question number 4, which is considering bicycle level of traffic stress. Now, this is a wonderful data set that MORPC maintains. You can see on the right-hand side, every road link is assigned a level of traffic stress. This goes from 1, these are the blue ones, all ages, bikeable for all ages, up to green, yellow, orange, and then red. Red are the limited access roads that don't allow bikes. These are the freeways. But we were specifically interested in how access to green spaces is impacted by the level of traffic stress that a bicyclist is willing to tolerate. And so particularly what we're going to focus on here is level of traffic stress number 4, which is labeled expert cyclist. So we're comparing access to regional parks with and without level of traffic stress 4. You can see down here an example of a traffic LTS4 road. Fairly large volume, high volume, or high speed arterial that even as an experienced bicyclist, you might not be comfortable biking on. And so we want to compare what removing these from the network would do. One note here, caveat, is that multi-use paths are not included in this analysis due to some data limitations that we ran into. So here's our final and 4th result, which is that we're comparing, on the left, we have level of traffic stress 1, 2, 3, 4, so including the expert cyclist. And then what happens if we remove that? And we just want people being able to bike on the all ages, most adults, to comfortable bicyclists. So sort of the first 3 levels of traffic stress. And here again, this is total regional park area accessible within a 30-minute time budget. So what we can see is that the impact is considerable, right? Once we remove those high traffic stress areas, we are not only significantly reducing accessibility to park space acreage sort of across the board, really, but we're also actually losing a lot. You can see a lot of areas that completely lose access, right? So all of these gray holes and gray areas here, they effectively completely lose access to regional parklands if people in those areas are not willing to bicycle on a level of traffic stress 4 road. So then we ask the question, well, what happens if we now add in transit, right? So on the right-hand side, we can see combination of bike and transit for level of traffic stress 1, 2, 3, but putting the bicycle on transit. And so that does actually make up for the loss of accessibility a little bit. We can see some return of accessibility in areas that previously got cut off because we excluded those roads. Now, one thing that we've learned here, and this is sort of a larger discussion, is how crossing one of those LTS4 roads is modeled, so not biking on it, but actually crossing it, that really does impact the results, right? So if you're saying biking on it is equivalent to, if we're not allowing people to bike on it, we're also not allowing it to cross that kind of road, that will have an impact on the results. So to summarize, what we've found here in this work is that, well, generally speaking, multimodal modeling with GMNS Plus really provides much more realistic accessibility outcomes. The network that we used can easily be expanded to surrounding areas thanks to this data standard, or it can be reused for other purposes. The key findings that we've made in sort of to summarize these 4 results is that, first of all, explicit modeling of walking access and egress really affects the results. In a simplified network, results are sensitive to design of connectors. Then biking to transit vastly expands access to green spaces compared to walking. Overall, the EJ TASs that were identified are slightly closer to the nearest green space on mode-by-mode basis, but the lack of auto access considerably reduces access to green spaces. And then finally, a combination of bike and transit expands access for bicyclists who want to avoid high-traffic, high-speed roads. All right. So that's all from my end. Thank you very much. Um, we have contact information here. We'll post this then later on. There's also a few links to the repositories, the GitHub repositories that are available for this kind of work. So,
Andre, that was so great. Super interesting presentation. There's a couple of questions in the chat for you.
mhm,
Sure if you can see them. Do you want to try and field them? Are we in the time that we have?
absolutely. And I do realize we are kind of running up against the time budget here, but
And
let
just
me
know we can run over. Like
okay,
if you have time, we can stay on for a
I
bit.
do. Yeah, absolutely. Um, okay, so let's take a look here. So we've been compiling the questions and looks like we've got a technical question here, which is unsure of M is something, but under step 5, both the transit and bike walk networks were prepared and merged. But what about the roadway network? So let's see. Okay, so this is step number 5 where we merge the networks. And the person who asked this question did actually catch something that I kind of glossed over here, which is that which networks we merge, that really is dependent on the modes that we are looking to analyze. Now, in this case, for what we are doing, we are actually not merging in the auto network. And as a matter of fact, the also walk to transit and bike to transit, the way that we are conducting analysis here with the separate networks, not with the allowed uses flags, that actually does require us to generate a different combination of network for each case, right? So bike to transit would be just integration of bike and transit. Bike and walk would be integration of those two. Now, if one were willing to work a little more with this attribute of the allowed use, that would sort of relax that constraint. But for our case now, we're not doing that, and so those are separate networks de facto. Right. Okay, let's see. Then we have, um, let me check quickly. Check the chat. Okay. So how would GMNS handle the coding of multimodal single occupant vehicle, high occupancy vehicle, public transit express buses, no trucks, barrier separated, dynamically priced reversible express toll lanes? Okay, so tolling information can be added as an attribute of a link, and the allowed uses field can be used to specify the modes that can use a link. When we're doing routing with DTA Lite, those mode-specific attributes can then be configured. There's a configuration file in DTA Lite that allows us to specify those mode-specific attributes. I will have to punt on some of the questions about like dynamic pricing, for instance, reversible express toll lanes. I know so that would be a question more for the US DOT team. But there definitely is the ability to have time varying attributes of the network. Actually, I see Scott Smith raise his hand. So he would be here and would be able to answer that question. Uh,
Uh, yeah, real. This is Scott. Really quick. Yes, there is the ability to have time varying links and lanes and segments. So that's how you would handle something like this.
But it's
Perfect.
not, I think, I mean, I might be interpreting Guy's question a little bit more
Yeah,
than, and maybe he can speak for himself, but there's not like the ability to, it would still be fairly manual where you would break up the time period and define those tolls. It's not like you would define oh, there's a dynamic toll here and it can range between this and this
correct.
based on speed. There's not like dynamic tolling kind of specification,
No,
right?
no,
Okay.
because we don't have the traffic volume, so we're not going to try to
Right.
reproduce dynamic tolling.
Right.
Yeah.
Okay, thank you. Um, do we have time for one more question? There's someone who's asking about bike stress, and I think that might be a question for Dave. How is that actually estimated?
Yes, I just replied in the chat
Ah,
with
okay,
our
perfect.
contact email for data and maps at morpsey.org. Um, it's a combination of using attributes of the link as well as community input. So we have many local stakeholders who have knowledge about roadways that go beyond the data that we have on file. But essentially, the more stressful roadways are associated with higher speeds, with more lanes, and I'd be happy to get to provide more detail from our documentation. And so I put our contact in the chat there.
Perfect. Thank you. So we have one more question here about in a multimodal network, is the model result sensitive to the connectors between different networks? Are these connectors auto-generated by the script or manually generated by users? So for now, at least, they are manually generated. This is a process that, in the future, we would like to have be an automated process. We do have an example Python script on GitHub that we provide where one can see how that's done. But in general, at least, I think, so we illustrated how the results differ with for different connectors to zone centroid connectors. That most likely will also be the case for transfer connectors. So for example, how much transfer distance we allow, or kind of what the radius is within which we're going to connect networks. So probably less than the zone connectors, but I do suspect that the transfer links will also have impacts on the results.
And if I could say, I think this is a great segue into the upcoming learning sessions because that's the second part of the question about are the connectors auto-generated or manually generated? That's a segue into the network tools. And so the next two learning sessions in this sort of family of learning sessions kind of pivot to the GMNS related tool sets, um, the ones that have been developed by ASU, and then the ones that some of the agencies are working on, Network Wrangler, to sort of satisfy MPO needs to build networks for static assignment, including projects and so forth. So anyway, that's a good plug for that. So please join us for those, and I think we'll get much more into those kinds of details then.
Excellent. Great. Thank you. All right. I think we are a few minutes over. I think we've covered many of the questions here, but anyone whose question has not been addressed or who would like to learn more or discuss more, feel free to send us an email. We're happy to answer any additional questions and go into some more depth on these things. So I think with that, we might want to wrap up, right?
All right. Thank you, Andre, Dave, everyone on the OSU team and the Morpsey teams that have been sharing this really interesting work today. I would love to, if I can, just pull up and share with you um, if you'll bear with me for one moment. Lisa, just a moment ago, referred to some upcoming um, uh, additional learning sessions, and I'm just going to share my screen to see if I can share those with you. Um, these are the sessions that, as again, I think I mentioned at the outset, this is the second of four GMNS sessions, learning sessions. Our next one will be coming up in August on some of the assignment tools, and then again in October on the Network Wrangler. If you go to these links on the Zephyr website, which you can see the link at the top, you can register for these sessions. And as I also mentioned at the outset, today's session is going to be posted. The recording and the links to the presentation will be available on the same events page under today's event. And I'd like to also maybe just call your attention to two additional learning sessions that we're going to be doing in a couple months. what we're calling the Taste of Momo. These are highlights from the Modeling Mobility Conference in 2025. We're going to be having a set of presentations next month in July, and then again in September. So we really encourage you, if you're interested, to register and attend those as well. Again, my thanks to everybody who presented today, and our thanks to everybody who joined us today. Thanks so much for being here for this learning session, and we hope to see you at future sessions too.